Yeah, thank you. So hope you can hear me correctly. We will discuss a little bit a topic, which is the identification of failure modes in column joints. Sorry, there is a T missing. Or what should be seen or can be seen as column joints. We'll see in a second. Quickly on review, okay. We will not present in this case our own experimental results, but we will focus on some quite known till now experimental results in literature. So what's the? Let me start from this. So in joints, no, there is this superimposition of a way we can see the joint, okay, or the anchorage in the joint. So the anchorage in the joint is an anchorage of the bar. Is this anchorage to be defined as according as a bar with its development length? Is it an anchorage as we see, let's say, from the perspective of anchorage concrete? Is it a joint shear failure? Is it all the same things and we should be seen as different types? Okay, this was to look a little bit in that. If we focus just a little bit on the development length, no? In reinforced concrete joints, it is okay addressed for a number of cases. It is, I want to stress, empirically expressed in SCI 318, very empirically. Okay, the equation is basically a predictive equation. It's affected by a number of things we know. And when we go and we want to see what happens in reality, we try to identify some failure mechanism, no? Which in particular will focus on concrete breakout and, let's say, joint shear failure. A premise. This is what we are talking about. And then if we see this as an anchorage, in Europe, in CEN, we recently changed our approach to the calculation of what is called here development length. And we know that the model which is introduced for some cases is a little bit, gives a little bit higher prediction with respect to the past, and can give higher prediction with respect to the ACI if we look at the length over bar diameter ratio in cases like that, which are quite typical. This is just an example for book. If we go to prediction of seismic, it's a little bit different, and things are a little bit more uniform. We'll never go out of this story of what is more correct or what to look at if we don't maybe make a reflection on what we are looking at. One thing about joint shear, okay, I'd like to show you this image because I think it clarifies a couple of things about joint shear failure. So these are some joint shear failure from past earthquakes in Italy, quite known images. It's why it's called joint shear, because it's a shear failure in the joint. This is clearly a shear crack. I always like to make people look at some things when we see like that, to be a little bit provocative. This is standing, so the structure did not collapse. So we also have to think that sometimes what we identify at brittle failure mode has some residual capacity. And for instance, if you look at a lot of tests made in the past on joint shear, when you have brittle failure in the joint, you see that the rotational capacity is not very low. So we can have still some resources. Of course, we don't want this to happen because the capacity of the structure associated with it is very low. But what's the point if we look at joint shear failure? I think if we go to the representation in more circles, it's very easy to see what is the point. So if the shear which acts in the joint is nothing more than the tension in the bar less the shear in the column. But since for ordinary structure, the shear which goes to the column with respect to the tension which is transferred by the bar is very low. I mean, we are in the order of 10%. Okay, in a matter of practical cases, you can disregard that. Okay, so it basically happens that you have to transfer this force, and if we look at this as the shear in a panel, it's this force over this surface, and this is basically our shear. Then we can have, okay, the contribution which comes from the axial forces. So as a matter of fact, we look at this, we can look at this panel and look at more circles. This would be the situation which we have in an iron force joint, and it happens if one on on this plane, okay, the inclined plane, you reach the tensile capacity, it's over, okay? That's very simple the end of the story. When you have, let's say, reinforced joints as we have today, what you can see is simply that you have a reinforcement here. So this point is not here, it's not the tensile strength, but it's the tensile strength plus the reinforcement, okay? So we enlarge basically our circle and we have more capacity, okay? But what is critical, of course, is that we may have a plane on which we reach tensile capacity. Okay. What we did, why did I need this slide like that? I mean, how testing was carried off in the past? Okay, we have a quite wide database of tests made mainly in the US with this type of configuration. And then this is, let's say, more generally used at the worldwide level. So in the beam column joint, if you extract from that, you basically pick a part, okay, of the structure, and then you assume that you have points of null moment, and when basically you have virtual curvature, and this can be representative of one piece of the structure which is extracted, okay? Now there is but this is hard to test, okay, and time consuming and whatever. So there are ways to simplify this, which basically look at this type, which is called the column type, the column type specimen. What you basically do is pulling. Now the assumption that you make here is that by pulling and barring, by restraining here, you're generating a moment which is equivalent to the moment which is generated here. And you can locate this support and try to induce a counterflexion. From this, we can observe some failures, okay? And of course, there are much more tests here than here, and these are used a lot to calibrate the equation for development length. So the scope a little bit of this presentation, okay, can we look a little bit better what happens here, okay, and try to identify which is the failure mode and what we are observing. So, question arises, which is the difference between concrete breakout and shear failure, okay, which comes from observation, which are the implications for non-design, because assuming that we can do that, okay, what does this imply? And bigger question, which is still unanswered for me to some extent, are we still in the context of the concrete cone mechanism? So what we make, we took some experimental results from literature. We want to see some specific tests where in those configurations we were tremendously far from any failure of steel or from any loss of addition. So we really could see something which the author identified as breakout. So big bar, big embedded, etc., etc. We considered the different failure modes. So we adopted a little bit this idea of the level of approximation, which now we use in FIB, where let's say first level of approximation is analytical, and then we make non-linear finite element analysis, okay, a little bit as a sort of validation. And we try to focus also on some tests for which we have some information, I mean, not only the maximum capacity, okay, some information regarding some point of measurement of strain, which could help in this validation. So we picked from among most of them some tests, we see that, for the beam column joint test. I will say large diameter, high strength steel, high embedment depth, with confinement, okay, in the sense that we had hoops, so 0.3% is quite a lot, and it allows, if you really see joint-shear failure, I mean, it's quite a good number, I mean, in terms of reinforcement, and high steel grade, okay, and so we start to also look at them and make some models. So the models were made in Athena with the rotating crack approach. The model is plain, and for two reasons. First, because the geometry, if you look at this is the domain thickness, allows you to say that you may have reduced effect, I mean, of the other plane. And then because in this type of problem, when you have low pressure, Professor Africa is not here, there is an interesting paper from some years ago, which were showing that when the air pressure is low, you can, I mean, basically have a simplification where the plane stress work, okay? So, helped by this, okay, we went on a little bit. we made this numerical analysis, checking, of course, mesh dependency, which can be quite interesting. In this case, just to show that we did not model this part because it was monotonic test, and this part gave a lot of issue from a numerical point of view. So we took this out. And making this assumption of bond. Since bond was not the main point, since unbonding was never reported, but we still want to capture a little bit, I mean, the transfer behavior, we made this simplification. So we modeled bond as a uniform bond layer, the intermediate to the bar, which has the same energy in shear, which comes from a bar which could slip and has this behavior which you already know. So this is an equivalence. Again, because the focus is not on steel, the focus is not on non-bond, we want, of course, to have the displacement associated to that, the load transfer, but not unbonding. Okay, so we kept this hypothesis. Which are the results? How much time I have? I can show some of that. So first, the crack pattern. The crack pattern is comforting in the sense that the crack pattern that was observed from numerical simulation is quite well resembles this picture which you see here from experiment. So this was identified, okay, as concrete breakout by the author. There are some details of the mesh dependency which I can discuss, but it's not very important. In the sense that even with the coarser mesh, you can capture maybe the capacity, but you don't capture well the load displacement, so you need some refinement to a given level to capture the displacement. But this was taken quite well. Also, comparing with some potential experimental measurement that were reported. Also here it's nice to see that the fact that there were some strains on the bar which activate, of course, when the crack starts, and also this was captured quite well in terms of when this happens. So this seems to work. The head pressure were very low, as we can see here. So what the analysis tell us? That okay, this nonlinear analysis matches quite well the experimental result. Okay, so we are looking at that. We see how we will use it. But if you look at the theoretical prediction, it seems that if we go with pure concrete cone, we are really low. Okay, in terms of prediction. If we evaluate in terms of anchorage length, according to the ACI equation, it works because, of course, it was calibrated also on this type of test. And also the prediction looking at the direction failure is work. But this was not used, let's say, to say, okay, the model captures. The model seems to capture global behavior, so we use the model to get more data. So if we want to understand, let's say, try to see, identify the failure, okay, let's see if how the panel behaves. So from the model validated, we use this approach, which we already used in the past, and was validated quite a number of times. So basically, numerically, what you can do, you can take a part. Okay, so for instance, you consider this zone. On this zone, you have a given variation of stress, but you can pick a medium average stress, and you can numerically derive the displacement and calculate which is the distortion. So doing that, you can plot basically a stress versus shear distortion, even if it was not captured from experimental point of view, and which has this type of behavior. This is totally numerically. Here, the only thing which is plotted is the prediction of shear failure in the joint according to analytical model, which shows that the things work quite well. And I think it's also interesting to see, at least in this type of test, what happens. And to me, this is not properly counterflexion, in the sense that you see this part which is rotated, you have this distortion which is related to the joint, so the joint is under distortion, but these other blocks are a little bit moving rigidly, so it seems that we have more a rigid body motion with respect to that. Okay. Another interesting thing, and then I will make some comments, is regarding this other type of test, where the authors varied the embedment depth of this bar. So there are a lot of tests, okay, where this bar has different length, okay, and we make all the numerical analysis and made the prediction. So according to, again, these three equations, which basically can say that. So the first equation is the joint shear, and you can see, okay, this is what we expect a joint shear failure. This would be, let's say, the anchorage failure in terms of development, and this is our concrete cone failure. Now, I'm on purpose here not reporting the potential increment that we have on the effect of bending moment, okay, to see how far we are, in the sense that how big should be, okay, the factor accounting for the bending moment, because if you make it simply analytically, this is almost square, and if for an almost square portion, your increase is 1.5, okay, so it's not very big. So this is, the prediction is plotted without accounting for the potential effect which we have for the confinement. What is shown? That of course, when the embedment is very low, we are here, when the embedment depth with respect to the emitter are very low, well, concrete cone really governs, of course, really governs. If we go far, actually, we see that joint shear failure, okay, the prediction accounting for joint shear failure, so the simple, very simple analytical criterion, the acting mean stress works quite well, and concrete cone seems to become unconservative, so we should account here for an effect of confinement to more than 2, to say that it is the size. This could be because actually what happens is that the problem is dominated by really a strat which is created here, and the formability here of this part is associated to something that I was saying before, that is as a distortion. I went a little bit quick because I think this session is full, and I'm done. 5 minutes. Yet okay, I counted on 20. Okay, good. So I may show something more here. Okay, so, and the same, some also useful numerical information can be extracted by numerical model. Again, you can see here, right? When the embedment is very deep, you have this strat which you created. This is really the failure surface. We are having distortion. Yeah, this is typical distortion you have in joints, okay? Where the embedment starts to be lower, okay, then we are having this other mechanism, which is what we are more used to assign, let's say, to a concrete cone. Numerical models, also in terms of tension in the bar, displacement, work quite well. I have to say that they didn't work very well when the embedment is reduced, or we tend, let's say, to a pure concrete cone failure, because after cracking, maybe it is too, the stiffness is not sufficient. This is probably due to the fact that this is a rotating crack model, probably with the fixed crack model in this case, you can pick the stiffness, but this depends also on the numerical result that you want. So which are the conclusions, which are the discussion, okay? First one, to my eyes, I mean, we have a need of having a better identification of failure modes in testing, okay? I think this distinction is quite crucial for an accurate assessment and design of beam column joints. We use two-level approximation, as I was saying before. First one just predicts the maximum tensile force, and the other one uses nonlinear numerical analysis. But of course, these are used as a sort of validation. From the numerical analysis, the crack pattern derived from the model are compared with in the test, and the major diagonal crack formation indicates shear behavior. Of course, you have a secondary crack that open in the test. Going to the main point, the analysis showed that if we just label that concrete cone type failure, it may be not representative of the actual failure mechanism in some cases. And the comparison which was carried out highlights a little bit the difference in the failure modes. But why I'm saying that? Because probably in the future, especially with respect to this aspect, we don't need to add the test in terms of changing configuration, changing, but probably we need less tests with more information, because we have a lot of tests, but typically the information that we have from this kind of tests are just the peak load and, if okay, I mean, the crack pattern. And if you scroll the database and you see some failures labeled in some way, then it may be hard, I mean, to use these in databases, okay? But to properly identify the failure modes, and also to see if we need to do something regarding the prediction associated to some failure modes, we need information from testing. So we need testing with more information, not hundreds of tests, but a few, where we know what we are observing, such that we can make some evaluation and give the proper label to what we are looking at. Since I'm concluding this and we are in this session and I have 2 minutes, as I was also saying in the presentation before the break, I used to go back to basic papers. And I was looking for another thing these days, and I got back in this paper by Rolf some years ago. How nice were the titles of that paper? Fastening elements in concrete structure, period, right? Okay, not this effect on that, period, okay? Why I want to recall that? Because some discussions are currently running in committees regarding changing this, changing that, changing a parameter. We don't have to change one parameter without looking at the entire framework, okay? Because things were developed consistently, right? And for instance, at those times, the basic model, what we're looking at, which are based on, we're looking at fracture, were clearly shown, okay, where there was an influence of fracture energy, okay? Which means we do not look only at concrete strength, or we may look only at concrete strength as a property if in this framework this is fixed, this is fixed, this is fixed. But if we are changing one thing, okay, we have to see if all the rest was developed consistently. Otherwise, we have risks because the models were formulated within some boundaries with some assumption, okay? So we have to know, I think, always try to be clear which is the basic physics of the problem, okay? And then see the application. But do not just change some commas in the application because this may be risky, okay? This may bring with that. So I think this was nice and I want to put on board. Thank you very much.